The broadcast is now starting. All attendees are in listen-only mode.
Hello, everybody, and welcome to today's webinar. My name is Matthias Brenner, and I'm currently in charge of sales for Europe at Friendship Systems. But as you can see here on the slide, I have worked quite a lot in engineering with CAESES for many years. So don't worry, today's webinar is not meant to be kind of a sales pitch, but I would rather want to focus on technical things and things that are directly related to the application of CAESES. So the topic of this webinar today is getting started with CAESES. And maybe I should point out that when I say CAESES, I mean both our full commercial version as well as the free version that's called CAESES Free. And in today's webinar, I would like to show you how to get started, how to best get started if you have purchased CAESES or if you have downloaded CAESES and registered for the free version. And I would like to give you the most maybe essential knowledge that you need during your first steps of using CAESES, as well as maybe a few tips and tricks along the way that might help you in these first steps. I think some of you might already be familiar with the basic concept of our software and its key capabilities. And for those of you that aren't, I would like to give a very short introduction, just a few slides of explanation of what the concept behind CAESES is. And please, if this is already old news for you, hang on, it will just take me a few minutes. And then after that, I promise that we will start going directly into the software right away. On this slide, you can see, maybe in one picture, an overview of what CAESES is made of. So what are the modules that are built within the software, and what can you do with them? This is the orange part here in the top is the part that is included in CAESES. So we have our block that we call upfront CAD. So this is the CAD modeling part. Upfront, as you can see here, is used quite often. It simply means that we characterize our software as a tool that is used rather early in the design process, maybe at a stage where your typical CAD tools are not necessarily already involved in the process, and we really want to focus on the geometries that are necessary for optimization and flow analysis and combining those things together. So the upfront CAD part of CAESES is made of the step of generating geometry. So you have quite a lot of functionality for parametrizing. They're also very complex geometry models, and then you would like to pre-process them so that they can be used in a flow solver, or maybe more specifically for the grid generation of your flow solver. So this leads us to the next step in the process, where external tools would come in. So in CAESES, we offer a generic interface that you can use to couple your arbitrary external simulation tools. There is a few examples here on the slide, as you can see. So it's not a fixed interface for certain specific tools, but rather a very generic one. And you can couple all kinds of simulation software. Apart from these commercial codes that are shown here, it can obviously also be in-house code or some other kind of tool that you have written yourself. Once the geometry is set up and your external software is connected, everything can be automated. And this is our last module, the so-called upfront optimization module, where you can set up post-processing to define which results you would like to get and analyze from your flow solver, and then define the optimization strategy. And finally, when you ran the optimization or a DOE or systematic variation, to assess all this data that you have generated. This next slide basically shows the difference between our full commercial version and the CAESES free, the free version. So you can see that most of the things I have just talked about are also included in the free version. So you can do all your modeling as well as connecting to external software. But the part that is taken out of the free version is the optimization part. So you're not able to generate variants, geometry variants in an automated fashion and actually run an optimization. So that's the main difference between the free and the full version. CAESES is typically used on all kinds of geometries or products that are somehow in relationship with the flow. So these are products that you would like to optimize in terms of their behavior and performance within this flow. And here on the slide, you can see a couple of examples of these geometries. For example, we have ship hulls or geometries that are inside of a cylinder of a car. This is also something that is related to powertrain, turbochargers, the impeller geometry, as well as the volutes that you can see here, or propellers, valves, wings, turbines. So all these kind of products where the shape of the geometry is very tightly connected to the properties and the performance that this product will have. And also, these are all geometries that have a more or less complex shape. So you have surfaces that have compound curvatures, so-called free-form surfaces. So things that are typically not so easy to parameterize in an efficient way in a typical traditional CAD system. Okay, that's it for the small introduction, just to give you an idea if you didn't know already what CAESES is all about. And now I would like to switch into CAESES, sorry, and show you how to get started. So let's assume you have just downloaded CAESES, registered maybe for the free version, and now you would like to make your first steps. So you probably need to know where to find information on how to use CAESES, where to get help on using CAESES, all these kind of things that would help you in the first steps. So the main switchboard for accessing all this information and receiving help can be found in the CAESES GUI in the so-called documentation browser, which you see open right here. So here you have a selection of links that will lead you, for example, to tutorials. So this is maybe something that that you would like to do if you to learn some basics, work through the tutorials. So we have some very basic tutorials that show you the most important things you need to know. And then there is also some more in-depth tutorials about more specific topics and also about modeling of specific types of geometries, or about connecting to certain external solvers like OpenFOAM or StarCCM, XFlow, as you can see here. So this is surely a good way to get started. Another thing you can do once you have looked at least to maybe some of the basic tutorials is we have a wide selection of sample files here within CAESES. So here you find samples for all kinds of geometries and project setups, from very basic geometry objects to also more complex full geometry models. So this is really yeah, a good location to look for solutions of how you would maybe model a certain more complex thing in CAESES. If if you're within this process of self-learning, you might need some help here and there. So there is different locations where you could get help. If you're a user of CAESES Free, you can go to our forum. So we have a dedicated forum for CAESES Free users. Obviously can also be used by users of the commercial version. But apart from the forum, the paying users of CAESES will also have the opportunity of getting priority support through our dedicated help desk, which is what you see here. Another location where you might find some tips and tricks and some interesting projects is our blog. So there is a link also here in the documentation browser. Obviously, you will also find the link on our website. So here is where we post some things that we find interesting or some information that we think is useful for users of CAESES. So this is a little bit of what is accessible here through the documentation browser. In a general way, if you are in the process of modeling or setting up a project, you might also need some very specific help about certain objects that you're working with. So let's say we have created a point during our modeling process, and we would like to get some help about this point object specifically. You can either press the F1 key or click on this icon in front of the name of this point, and this will lead you directly to the documentation of the point object, which gives some explanation as well as specifying certain commands and functionality that can be accessed for this specific object. So this mechanism is available for all kinds of objects and things that you're doing in CAESES, either through the F1 key or pressing this button as I showed. Obviously, you can also go through the search here in our documentation browser or look in the type list, where you can also find all geometry types and so on to access these documentations. Another thing I would like to point out here is that obviously if you're getting more serious about CAESES and would like to know more or learn more in a quicker way, keep in mind that we also offer trainings, either individual training on site for customer, but also group trainings that we offer here in our premises that will happen from time to time. So that's also a way of joining one of these trainings and get to know more about CAESES. So let's go from here now to from, so to say, the general information of how to get started to a live demo where I would like to show you say the first steps of setting up a model and giving you a little bit of basic knowledge that you need for that. The idea here is that we want to build a simple geometry model. As you can see in the picture, this is supposed to be a duct that is swept along a specified path, and this duct has a parametrized cross-section that can be varied along the path of the sweep. And at the end, when we have set up the model, I would like to show you also quickly how to make it ready for an automated variation and how to run this variation. So let's go back to our graphical user interface. And there is mainly three windows that I will be using in this live demo. So there is a lot of functionality in the user interface, but for now, I think it's enough if we focus on these three specific windows. The first one here on the very left is the so-called object tree. Here we will see all the objects that we create, geometry objects and other things, organized in a tree. So it's very similar to like a directory tree that you might see in an Explorer or something like that. So this is gives you the overview of your project and also a way of organizing and sorting all the things that you have included in your project. Then the next window here is the so-called object editor. This is the location where, when you have selected an object, you will be able to access the properties of this object and change the properties or simply have a look at them. So you will see in a minute how that looks like. And finally, here on the right, we have the 3D view. This is a 3D window where we will see the geometry when it's modeled, and we can rotate it and so on. Everything that you know, I guess, from other modeling tools too. So I would like to start now my modeling process by defining the path of the duct that I have just shown. And for the definition of the sweeping path, I would like to use a so-called F Spline curve. And this is a special curve type within CAESES. So I would like to give you a short introduction, just so that you understand what this is about. This is a proprietary curve type that is available in CAESES that we have implemented. And it's a very useful curve type, I think, for parametric modeling, because it's a curve that is also that is already parametrized, and also it is a fairness optimized curve. So it has an internal fairness optimization to make sure that it has a very smooth and fair shape. And this is usually or often something we are interested in when we're dealing with flow-related geometry, that we would like to have a smooth geometry. So this curve type is a planar curve, so it has to be located in a 2D plane, and the minimum requirement is to specify a start and end position of the curve. And of course, if you specify only the start and end position, you will get a straight line, because that's the smoothest connection between 2 points. So you can then start adding more parameters or more input. For example, as we see here in the picture, you can specify the tangent at the start of the curve or the tangent at the end of the curve. You can specify the area between the curve and one of the axes. So you see here there's two possible areas we can specify in this example. And if you have specified the area, you can also additionally specify the centroid of this area to define how the area is distributed under the curve. And the curve will basically take this input and run an internal optimization to be able to fulfill these parameters but get as smooth shape as possible. That's the idea about the F Spline. Okay, so let's go back to the user interface and start creating our F Spline curve. So I will go to the menu and create this F Spline, and you see that this object now shows up in our object tree. And since this curve is currently selected, we see the properties of this F Spline curve in our object editor, as well as the view here in the 3D window. As this is a planar curve, as I said, I have to specify the plane it should be located in. In our case, we are working in the X plane, as you see in this view. So this is the YZ plane. And as I said, the minimum requirement for the F Spline is to specify start and end position. So now I'll just slightly change this. So now we have a curve that goes from the origin to the position 0, 1, 1 in a straight line. So now I would like to add some additional input to this curve. So for example, I want to specify the start tangent as 90 degrees. So this will give me a vertical start of the curve. And the end tangent could be maybe 10 degrees. So you can see how these values that I entered here are being fulfilled by the curve that is generated, and at the same time we're getting the most smooth shape that is possible with these parameters. So another thing I might want to do now is rather than just entering the value here for the end tangent, I want to select this value and create a parameter here. Let's call it end tangent. So we have now a parameter object in our tree here, and our F Spline curve references this parameter now here as an input for the end tangent. So this is one way of creating a parameter in your geometry. So I have entered the value and then selected the value, and with a right click created the parameter. Let's say now I would like to specify another parameter for the area below the path, so of the area between the curve and the y-axis. So I specify my area axis as y, and you see here a preview of the current value of the area, 0.73 something, and let's say we want to set it at 0.75. So you see the shape changed slightly, and now we can create another parameter here for the area. Okay, that should be enough for our path. I will just change the name of the curve to path. That's maybe also something to keep in mind, that when you're modeling, you will create in a complex model at least quite a lot of objects and curves and points and surfaces and so on. So it's always a good idea to assign some meaningful names to these objects, so that if you open the project at a later point in time, or if you give it to one of your colleagues, that it is understandable what means what in this project. So another thing that's also connected to organizing your project is that you can create a folder structure. These folders are called scopes in CAESES. So now, for example, I want to select my path curve and the two parameters that I have created, and I create this scope and call this also path. So now you see we have a kind of a folder here in our object tree that contains all the objects that are related to the path, and I can collapse it here so that I can also create a better structuring in my project and make it easier to find things. Good. So now we have defined the path for our duct. So the next thing we would like to do is to generate a parameterized cross section through this duct. It's not going to be very complicated here. So I would like to use an elliptical cross section. So I go to my menu again and create an ellipse. So maybe you can see now we have quite a large ellipse, or circle actually at the moment, because the two axes have the same length. So this might be a little bit big. So let's say we want the one axis to be 0.2 in length, and again we can create a parameter for that. The name should be, let's call it radius. And now for the length of the second axis of the ellipse, I would like to reference my radius parameter and multiply it with a factor. So let's say axis B is radius multiplied by 1 for now. So that axis is also scaled, and this factor that I have multiplied here, I would also like to create as a parameter. This is the radius factor, should be the name. So you can see here where I have specified this expression just now, that all the editor field that you have available for the objects here can hold a discrete value, but you can also enter alternatively an expression that will give you a value as a result. So in this case, I'm using a mathematical expression. Can also be other kinds of commands that get a certain value from another object, things like that. So whenever your expression gives you floating point value as a result, you can use it here. All right, and let's just name this curve section. And now we have specified our cross section. The parameterization we have done to the cross section is that we can change the size of the two axes of this ellipse. And now another thing that we would like to do is that, of course, rather than having the cross section fixed here at the start of the curve, we would like to be able to sweep it along this path that we have defined. So what I will do is select my original ellipse and create a so-called image curve. An image curve is a kind of a copy of an original object. So you see it references my initial section, and on top of that I can add a transformation. So in this case I would like to take my cross section and transform it to a certain position along this path. So what I can create here is a so-called sweep transformation. In the sweep transformation, I can define a specified path. So I can either take my path here and drag and drop it here, or another option is also to hold the Alt key and click on the path object. Then it will be entered in that editor field. And additionally to the path, I can also specify the position along this path. So let's say we enter a value of 0.5, then the my curve or cross section in this case is translated and moved to the relative position 0.5, so at the half of the path. If I use 1, it will be at the other end. 0 is at the initial end. So specifying a value between 0 and 1 will move it to the corresponding position along the path. So let's call this transformation to pos, because it moves to a certain position, and we would like to create a parameter for the position along the path. Call it pos. And finally, my image curve should be called at pos. So this is my cross section at the correct position along the path. Okay, so why did I do this? Because this is, so to say, the template with which our surface will be created for my duct. And here I have another short introductory slide. Sorry, here it is, about what we call a metasurface in CAESES. So again, this is a proprietary geometry object that we have implemented into CAESES, and is really one of the most powerful tools that we have in CAESES for modeling, because it gives a very nice way of creating an efficient parametrization also for very complex surfaces. So the idea here is that we start the surface modeling with definition of the cross section through the surface. So we set up a template of how a cross section through the surface looks like, and this cross section will be controlled by certain parameters. So in this example, we have a profile section, and one of the parameters is the chord length. In our live demo just now, we have an elliptical cross section, and the two parameters are the length of the two axes of the ellipse. And now, rather than creating individual copies of that cross section, a discrete number of copies, and setting discrete parameter values, and then lofting a surface through it, we were going a slightly different way, namely by saying, okay, this is the template, and now we can define continuous functions in the direction of our surface that specify how the parameter value of this specific parameter changes while we go along the surface. So here in this example, we have set up a distribution function that specifies how the chord length will change in the span direction of this wing. And if once we have created these two things, we can connect them to each other, and then we are able, with this information, to generate the surface. So we have a complete mathematical description of the surface. We don't need to loft through a discrete number of sections, but we can do a kind of a continuous lofting of this section. So let's go back to CAESES and see how that looks like in praxis. So I have now created my cross section and specified the parameters that control this cross section, and now I can select all the objects that are part of this cross section, and while not selecting the input parameters to it. So now I've selected the initial ellipse, the translated ellipse, and the transformation and create a so-called feature definition. So using here the menu, new definition from selection. So this will now create a definition of this cross-section. You can see this is like a small script or like a macro, maybe something like that, that specifies I have certain input parameters, the radius factor, a path, and the position along this path. And with this input, I create certain objects that are then output of this feature definition. Let's call this feature definition duct section. Oops. And yeah, these are our arguments. Assign a category here. Of course, these feature definition that I have now created automatically from a selection can also be created manually. So if you have a certain, let's say, affinity to scripting or to coding, then you can obviously also write this definition by yourself without having to model it first and then creating it from the selection. If you're not a big fan of scripting and so on, then you can follow the way that I have just shown you. Also, maybe if you're a beginner and are not so familiar with the commands, then it might be the easier way to go. Okay, we're gonna save this definition. Now I can put all these objects here that I needed for the generation of the cross-section into a folder. I will call obsolete because I don't need it anymore. Now I have translated all of this information into my feature definition. And now comes the, say, the second step. This feature definition is basically the template that defines the cross-section of my surface. And now I would like to describe how this cross-section changes along the surface, how the parameters of this cross-section change. So what I need to do is create a so-called curve engine. Here I select my cross-section definition, select a curve from this definition, and now the coordinate system for my distribution functions that I will define in a minute. And now maybe let's start with some constant values here for these parameters, radius factor, also constant to 1. Our path is this one, and the position along the path should be the first thing that we want to set as a variable value, because obviously to create the complete duct, we have to change or vary this position from 0 to 1 so that we achieve the sweeping of the surface. Yeah, to make this value variable, we will just create a curve for pos, I will call it, that goes from the origin to 1, 1 in our x-plane. So basically this curve will give us at a certain position between 0 and 1, it will return the same value. And if we enter it here for the position, call this curve engine for duct. And now we are able to create our metasurface. And our metasurface uses now this curve engine. So the curve engine is the object that supplies the section at a certain position for the surface generation. And in the Metasurface object, we specify we want the surface to be generated between 0 and 1. So you can see now our duct is swept along the whole way of the path. If you would want to say we just want to create a surface up to the half of the path, then you can just say the end position should be 0.5, and then we get this shortened duct. But we want the whole thing here. Maybe we increase the resolution of the surface a bit to have it a bit smoother in our visualization here. So now this surface should be called duct. And now we have specified just constant values for radius and radius factor along the complete path. The only thing that is now variable is the position along the path. Otherwise, we wouldn't have been able to create any surface. And now, of course, we can change these constant values, and then the whole duct will change in shape. Or we can say now the radius shouldn't be constant, but we would like the radius to vary between certain values along the path. So we create a function, distribution function, again in this plane. Maybe I make my duct surface invisible for a moment. We would like our radius to start with a value of 0.2 and end so the y equal to 1, we would like to end it with a value of 0.35. Maybe give it a start tangent of 0 degrees to this F spline in the right plane, end with 0 degree. And now you can see here this distribution function we have created that describes at the beginning of the path, at the position of 0, we have a radius value of 0.2, and then the radius gradually increases until at the end of the path, at the position of 1, we have a radius of 0.35. The start value and end value we can set as parameters again, so that we can control this distribution function through these parameters. So I created two parameters at start, at end, and this should be our function. Put everything into a folder which we call radius. And now if we visualize the surface again and go to our curve engine object, rather than specifying the constant value, we enter our distribution function here. And you can see now that now the duct starts with this radius of 0.2, but now it increases in diameter and it ends with a radius of 0.35. Let's just copy and paste the whole thing, our radius function, and the pasted copied object should be our second function that controls our radius factor. So I will rename this folder, and we would like our radius factor to start with a value of 1 and end with a value of 0.5. And now we can go to our curve engine again, and for the radius factor, replace the constant value with our new function. And now you can see, oh, I did it the other way around as I actually meant to do. Actually, I wanted to specify at the end a factor of 0.5, and at the start a factor of 1. So you can see how that influences the geometry. Okay, so this should be our very simple geometry model. Of course, this is not necessarily something as complex as the examples I have just shown in my presentation, but at least it gives you, in the shortness of the time, a quick overview of how to use this so-called metasurface to model a surface that should be controlled by parameters. And once you have set up the model, you can of course start varying the geometry in an automated way, which is what we can do now. So let's say we would like to change the radius at the end and at the start. So we switch these parameters to design variables. So we say these should be design variables for our optimization. Maybe also the radius factor at the end of the curve should be a variable. I think that's enough for the moment. And now we can set up an optimization or DOE engine. In our case, I will just use a DOE using a so-called Sobol sequence that varies the specified design variables and creates a specified number of designs. So the design variables I wanted to use were the radius at start, radius at the end, and the radius factor at the end. I can now specify bounds for my design variables. So this should go between 0.1 and 0.25 maybe. The radius at end should be varied between 0.3 and 0.5. And the radius factor maybe between 0.25 and 0.8. So these are the bounds for my variables. I would like to create 20 variants. And to be able to compare the variants to each other, I would like to create some screenshots. So maybe create a screenshot collection. Would like this screenshot. Let's have a preview. And maybe another view from here. Preview. Looks okay. And now we can run this variation. Maybe save the project somewhere. And run. So now we can see in this table view that the design variants are being created. We see the values of these design variables, of the 3 design variables for each design that we're creating. And now it's finished. So now what we can do is open these designs in the so-called design viewer. That's the button that I'm selecting right here on top of the table. And in the design viewer, I will now see the 2 screenshots that I created for each of the variants in direct comparison to each other. And here at the bottom, I also have an interactive 3D geometry that I can rotate or pan and zoom in and zoom out, so to give me a good comparison of the variants to each other. So I have the option of comparing, of course, the numerical values of the variance, but I can also compare the variance visually. Of course, everything here gets more interesting once you also include some simulation into your process, which we don't have right now. But if you ran some simulations for the variants that you're creating, then you will also get the results values from your simulation here. You can sort your designs by these values to look for the one that has, for example, the lowest pressure drop if it's a duct like this. And also in this visual comparison, you can add post-processing pictures that show simulation results, so that you can also do a side-by-side comparison of the flow field of the different variants to get an idea why one of the variants might be better in its result than the other one. Okay, I think that is so much for a first introduction into CAESES. We're coming to the end of today's webinar. So the idea today was to give you a short introduction into what CAESES is all about, to give you some basic information about where you can find help and tutorials and things like that for your first steps. And the idea of this live demo was to familiarize you a little bit, just a little bit, with the graphical user interface of CAESES, and show you some very basic things like how to generate objects, how to create parameters, how to parameterize geometry in general, how to start a variation. And I hope that has been useful or helpful for you and for your first steps with CAESES. So I would like to thank you very much for joining today's webinar and for your attention. And please follow our news on the website for upcoming webinars. So we will have at least once a month, we will have some more webinars, and the next ones will focus more on specific topics like connecting CAESES to external simulation software like OpenFOAM, that's an upcoming webinar, or Converge CFD, that's a commercial flow solver. That will be the next webinar in February. And we will also have other webinars for other specific topics or specific applications and industries. So yeah, make sure to see what's coming up. And of course, we would be happy to have you join if that is a topic that is interesting for you. One last thing I would like to point out is that at the end of this webinar, once I close it, there will be a very short survey, might take just 2 minutes or so. So I'd, of course, appreciate if you take these 2 minutes to answer the questions that pop up there. And otherwise, I'd like to say goodbye and hopefully see you soon in one of the upcoming webinars. Bye-bye.